Hello all, welcome to this tutorial in which now we shall be coding the state of the art idea of diffusion models. Okay, so this is a very simple image that will show you the forward and then the reverse process that has been discussed in the diffusion model. So now this is the forward process in which for x naught you'll add some noise and get x1 so on and so forth. You t minus 1 you'll add some noise, you get xt. To that you'll add some more noise, you'll get xt plus 1. Now so on till a very large step t. So you convert it into a normal distribution with mean 0 and then the variance I. Now, this is what is called as a forward process in which you will not be having any trainable parameters. Okay. Now, these is not having any of the learnable parameters. That doesn't mean to say that this is a deterministic process. This is a probabilistic process. No, because you will be sampling from 0i. Okay. This is not a deterministic process. This is a probabilistic process. Okay. Fine, good. So now this is regarding the forward process. Now coming to the reverse process. Okay. So now you will be from the Gaussian, standard Gaussian, you will be going back till you get the x naught. Okay. Now, as has been discussed, now this idea that we have is not a sampling procedure as we saw in our earlier discussions of GAN or VI. This is a denoising procedure, and then for sampling, now we will see another procedure. Okay, so now how do you sample? Okay, now once you have done that, now you perform the full reverse process. You take it from standard Gaussian and then you perform every step in the reverse process now till you get either mu theta or x theta cap of xt. Okay, whichever. So we have seen two formulations. Whichever formulation that you are having, yeah, depending on that, you will be computing the new image. So now, as we have seen that the generation here is actually time consuming now because this has to pass through all of these processes in sequence, unlike GAN or VAE, where in which the generation of novel data is actually a one-step process. Okay, so now let's look at the training procedure that we have. Now we shall be using the unit architecture. Now you should be aware of unit architecture as now we have discussed it in our earlier tutorial. Okay. So now how do you perform the training? Okay. Now in the training process, now you take an input data or you take a batch of input data. Okay. So then what do you do? Now you should remember that in our elbow. So where did we? Yes, here we have yes. So in this formulation or the equivalent formulation where which you have x theta, no, that's fine. So now what you will be having is now you will be having an outer expectation. Okay, so now that is summation t is equal to 2 to capital T. Now you will be having this term, and on top of it we have taken only one point. Now you need to take a batch I is equal to 1 to some n. Now there will be having two summation terms that needs to be looked into before just finding the mu theta without just calculating before calculating the mu theta. So there has to be a two more summations that we should take into consideration. Okay, so now this our discussion here is with respect to only one data point. So we should add one more outer summation. So in our training procedure. Okay. So now you pick a t or you pick a bunch of t's. Okay. And then you will be able to obtain xt of m, which is a straightforward computation. You know x naught now because you have sampled from your data, that is your true distribution p of x naught, you have sampled from there. So now you know x naught, and then this alpha t bar, now these are the pre-computed value. Even this is a pre-computed value. And then epsilon t is what you are sampling from the standard Gaussian. Okay. Now obtaining this is a pretty straightforward thing. Now once you have got that, now then what you are supposed to do, now you should go ahead and perform the weight update. Now how do you do perform the weight update? You have taken a bunch of t's, okay, and then for each t you would have got some outcome from the model, okay. And this is what you would have gotten the outcome from the model. Now you calculate this using this equation. You calculate this term using this equation and give it to the unit architecture, and then you get x theta cap, and then you regress it with your data. Okay. Now this is for a bunch of time steps. So now again, this you should be doing it for, let's say j is equal to 1 to n. This you will be doing it for a batch. And then you will be updating your weight as per batch statistics. Okay. Now this is the overall, the training procedure that is there. And then in addition to that, now whenever you are passing this xt over unit, you will not be just passing xt, you will be passing t in addition to it. Okay. Now there are multiple ways of embedding this t. Now if you just put xt and if you consider this as a vector and just add t as a scalar, see what happens is your xt is in a higher dimension, so your t may be ignored actually. Now because of which what we should do is now we should make it into a preferable size and then add it. Okay. Now there are multiple ways of adding this embedding. Now one way that was discussed in our theoretical sessions was using the sinusoidal embedding. Okay, which is sinusoidal positional embedding. Now which has been used, yeah, positional embedding, which has been used. Now, there is one more even simpler way of doing it. Okay, so now we will be using that in our code. Now what we shall be doing is, now consider that the t that you have got is 5. Okay, and your image size is 4 cross 4. Then what I'll do, 5 5 5 5 5 5 5 5 5 5 5 5 5 5 5 5, and I consider that is a single channel image. Now what I'll do, I'll add this to that channel. If it is a multiple channel image, let's say that your number of channels is 3, this is plus 1, so your input will be a 4 channel thing. If your input is only one channel like MNIST that we shall be using, so you will add this one channel of positional embedding to it, because of which your input will actually be 2 channel input. Okay, now this is how we shall be doing the positional embedding. Now we'll be taking MNIST dataset, which is of size 32 cross 32 with one one channel. So now what we will do, we will make it 2 32 32. Now that means that you will have a 32 cross 32 block, now in which these t's are there. Okay, the same value of t is there. Okay, now if you replace this with the sinusoidal embedding, yeah, this is one more kind of embedding that you can do. Okay, that is what we shall be doing. And then you perform the forward propagation and then the backward propagation. Okay, so now please remember that now to this you should add one more term. Okay, so now during our discussion we are only considering this third term, which we have actually done. So let's go back. You should be considering this term also. Okay, you have only considered this term or equivalent of this term. You should also be considering this term. Now how do you do it? It's pretty much simple. Now you take x naught and just pass it over t is equal to 1, and then you get x theta t is equal to 1. So and then you can find the MSC in that case, and then add it to the term that we have obtained and then back propagate. Okay, now this is what we are supposed to do. So now let's see this in equivalence with the code. Okay, so now so now due to some what do you call computing constraint, I was not able to do it in Colab. So what I have done is I have used my own personal system, and then the same Colab I have downloaded. The same file will work in Colab. Okay, it is just the computing restriction that was there which did not allow me to do it. Okay, so now here you have the necessary libraries. Now, we have looked at these libraries multiple times, so I shall not be going into it. Okay, and then you have t is equal to 1000. Now that means that now you will be, let's go back and write these values. Okay, now what we shall be taking is, now we are taking t equals 1000. And then now we need alpha values. Now, what normally they do is they will not calculate alpha directly, but they will use something called as beta. Okay. Now, beta is a value that we shall be taking, between 10 to the power of minus 4 and 2 into 10 to the power of minus 2. Okay. Now, this belongs to this range. This is beta. So now, what is alpha? Now, alpha is 1 minus beta. Now, because of which, evidently, now alpha will be more than 0.99. Okay, that is what we actually wanted, right? Now, if you remember our discussion, alpha t is fixed between 0 and 1, now preferably 0.99 onwards. Okay, yes, now that's what we have actually achieved. Okay, so now here beta is not a single scalar. Now it's a vector. Now having 1000 entries. Now because you should be doing it for all the t things, right? Now you want alpha one, alpha two till alpha capital T. That is what you're doing. You're doing 1 minus beta, because of which you get your alpha values. Okay. Now and then in addition to that, you want alpha t bar. You'll be needing this alpha t bar, which is nothing but the cumulative product at each step. Yes, that is what has been done here. You take alpha and then you take the cumulative product. Okay, so and then you will also be needing and one more term. Now this is square root of alpha t bar. Now if you can just go back and look at these things, whether see, you need, this is cumulative, this is single alpha, this is square root of that cumulative. Okay, so now you shall also be needing square root of that cumulative. The 1 minus cumulative square root also you will be needing it. Now these are the values that we need. Now that is what I am doing. Now 1 minus, now this I am doing it for all t. Okay, that is what is here. Okay, so now that means that all the values that you need, alpha t, this is beta t, all these values are pre-computed and ready. And these are the values that you shall be using in your forward process. Now, since these values are ready with us now, so now this is uh, the process which doesn't have any learnable parameters. Now, these are the parameters that are fixed by the user. These are hyperparameters. Okay, so now with these things ready, so now then what I'll do is I'll use a unit. Now unit architecture I'll not be explaining much now because we had a seen in our earlier session. Now you need the in channel is 2 in this case specifically. Okay, now you can modify it. You just modify it here. Now apart from that, the outcome is almost the same. Yes. Now your input is a uh, so what is your input? Now your input is, let's say that 1 comma 32 comma 32. Your output is also 1 comma 32 comma 32. Okay, so now unit, what you will do, now you will see a gradual reduction and then you have a bottleneck and then you see the increase. Now in this case we use conv layer and then we use here transposed conv layer, and this is what is called as the bottleneck. Okay, now we have seen this in our earlier tutorial discussion. Okay, that is what you see here. Fine. So now here, please consider that now you're passing the input post embedding your post embedding your position actually. Now that is the reason why it takes two in our case. Okay. So now let's put it all of them together, and then let's get the values of uh, let's get the values of these. So you have the unit architecture, and then you are storing all this beta, alpha accumulated, square root of alpha accumulated, and then square root of 1 minus alpha accumulated. Now all of them you are putting in the register so that you can use it whenever you want. Okay. So you have moved it into the device. Okay. Whenever you have the register, you can move it into the device. And does this equation seems familiar to you? Now, this is your xt. Now you want to calculate this xt, right? Now if you remember, yeah, here you want to calculate this, right? Yeah. Now accumulation, square root of accumulation, square root of accumulation, and then square root of 1 minus accumulation, yes, into the noise that you have. Okay, this is the formula that is there. Now this into x naught plus this into the noise that you have obtained. Now this is exactly this equation. Okay. Now this is how do you get xt. Now we know how do you get xt. This is one method that is being used. Now let's go into the forward process. Now let's go into the forward. So that is learning. Okay. You have your x. Yes, that is ready with you. So then you have to pick a t. Okay. Yes, that also will be sent to you. Here, x naught and t will be sent to you. Fine. So now once you have that, now then you want noise. Now why do you need noise? Now this term, epsilon t, is what you need. Now you have generated the noise like x naught. Now that means that it is the same shape as that of the x naught. Now you want to get xt. Now how do you get xt? Now, x naught comma t comma noise. Now this is what you get here. You get the value of t. This t is a scalar. Okay. Now, this is not your embedding. This t is a scalar. Please remember that. You're indexing it here. This is not a embedding. This is a scalar. So now you have got your xt. Okay. So now this term is done. Okay. Sorry. This term is done. So now what you are supposed to do? Now you have got xt. Now you have got this. Sorry. Now this is done. Xt. Now you have to take this xt, pass it through the unit, and obtain this value. X theta hat is what you want to obtain now. Yeah, that is what you are doing. First, you are getting x naught dot shape. You are getting b, h, and w, and you are getting your embedding. Now, as I told you, if it is 5, yes, you will have. If your time is 5, you have 5 all over here. Now that is what this command is doing, and then you are concatenating your xt, now which you have obtained, and then the position, your dimension 1, and then you are passing it through unit. Now once you pass through unit, now what will happen? Now you would have passed this here, and then you obtain x naught hat. Okay, and then you obtain the MSE of it. Okay, that's what you want, right? Now finally you get this, and then you obtain the MSE of this. Okay, now this is what one specific example or one specific batch. Now that is there. Okay, so now this is your forward process. So now let's look at the sampling. Yeah, and then you will be going ahead and doing the in your training. You'll be zeroing the grads out. All those things will come later. Let's go in sequence. Now your inference, which is your sampling. Now how do you do? Now you have to do it over all things. Okay. To do it, no, it's not like you have a specific T for which you should be doing it. You should be doing it for all the things from. So if you can look at it here, Now from the standard Gaussian that you take, you should be following all the steps. Now that means that you should be iterating from t minus 1, t minus 2 till 0. Okay, now you should be iterating till that point, yes, or till 1, sorry, till 1 you should be doing it. That is what you are doing it here. Reverse range. Now that means that you are getting t minus 1, t minus 2 till 1. Okay, now first you have got the x now, which is the same shape as that of the data. You would have got it from the normal distribution. Okay, fine. So now you are getting the T. Okay, now whatever is the batch size, you are getting it, and then you are extending it. So now to this, you have concatenated your uh, embedding. So now your X, now whatever time position it is, now that's mandatory for us. Let's take, now it is the initial thing, you would have gotten this. And then you pass it through unit. Now, because we are using the same unit for all the timestamps. Now, it's not like for each timestamp we are using different units. No, that is not the case. Now, we are doing it for all the timestamp together. So now what you do, you obtain this. At this step, x t minus 1 is what you get. Okay. Now, good. Now then, what you are supposed to do? Yes, you got x naught hat, but do we need to stop at that point? No, right? Now, if you remember our uh, discussion, okay, now you get this value, okay, you get this, yeah, you get this xt hat, so the x theta hat. Now then what you're supposed to do, now you have to obtain this parameter, right? Okay, now that is what you're trying to achieve it here. Okay, xt minus 1 is from a normal distribution of this. Yeah, you achieve this, and then you clamp it between 0 and 1. Now finally the same equation is being repeated here. Now you clamp it between 0 and 1. Now this is your inference process. Fine, quite easy. Now the training is, first you port everything onto the device, obtain the data loader, blah blah blah, the same thing. Now you obtain the model, you get the optimizer. Now you're running it for 15 epochs. You're keeping track of all the losses so that you can plot it later. Yeah, so and then you're keeping your model in the training loop. Fine, and then you take a loader, you take one batch of examples, you put it onto the device. Okay, now sample t from 0 to t. Okay, now that means that you're sampling 1t. Now here t is a scalar. You're obtaining for a specific timestamp, and then you're passing it, and then you get the loss. And please see here, I haven't taken a batch of t. Now actually, you should take a batch of t here. I should not be taking a single t. Now that means that you should be repeating it multiple times. I have left to you. Now I just want to include one more loop here and then see how the result changes. Now I have done just taken t is equal to one value, any value that it comes. So and then I'll pass this through the model. The model will give you the loss. Now why the model will give you the loss? That is what you have defined it. You get x naught and t. So and then you obtain the sample. Okay. So and then you get the for that specific t you obtain xt, and then you get the positional embedding, and then you concatenate it, pass through the unit, and get your x naught hat. Now get that x naught hat, and then compare it with using x naught via MSE loss. The loss is coming here. Okay, and then you zero grad it backward and step. Yeah, standard procedure, and then you keep the bookmarks. Okay, fine. This is your loss curve, and then finally I'm doing the inference. I want 16 samples. Yeah, I'm sampling it. So the samples now will, as we discussed here, you'll get the samples from this method, from this function, and then you, yeah, bad generation, right? Correct. This is a very bad generation. Why? Okay, I'll tell you a couple of reasons for it. Now, what is the first reason? The first reason is here. You're not taking a bunch of T's. Okay, you're just doing it for one T. Here, you would have taken it for bunch and then added them up. You're not doing it. And then Now, where is the first term? You have missed the first term. Actually, you have done it for only the third term. Your back propagation is done only for the third term, because of which your weight updation is not proper. Okay, but even then, with the small number of epochs, like 15 epochs, yes, no, it is generating some images. That's fine, no problem. So now you have to add all of them, so that you get better samples. Okay. Now please remember this. Now here, the way to sample is to go through the whole reverse process without leaving any step. Now that is what we are doing here. Okay. So with this, we conclude our tutorials on DDPM. So in the next tutorial, we will be implementing some other formulations of DDPMs. Thank you.